Welcome to Module 3, Systems of Linear Equations. In this module, we'll explore the representation of linear systems as matrices, Gaussian elimination, and matrix row operations, and various methods for solving systems of linear equations using matrix approaches. We begin with the foundational concept of representing linear systems as matrices. Consider a system of m linear equations with n variables. Each equation can be expressed in the form given for all m equations. This system can be elegantly represented in matrix form as Ax equals b, where A is the coefficient matrix, x is the column vector of variables, and b is the column vector of constants. This matrix representation is pivotal in solving linear systems efficiently, particularly in AI applications like regression and optimization. Gaussian elimination is a fundamental technique for solving systems of linear equations, by transforming the augmented matrix through row operations. These row operations include swapping rows, scaling a row by a non-zero scalar, and adding or subtracting a multiple of one row to another. Gaussian elimination's primary objective is to simplify the augmented matrix into row echelon form, or reduced row echelon form, making it easier to solve the system. This systematic approach is crucial for solving large systems efficiently and is a foundational concept in linear algebra and AI. Let's put Gaussian elimination into action with an example. Consider the system 2x plus y equals 5 minus 3x plus 4y equals 2. We'll represent this system in matrix form and apply Gaussian elimination to solve for x and y. This example illustrates the practical application of the techniques we've discussed in the previous slide, providing you with a clear understanding of the process. Continuing with the example, we apply Gaussian elimination to the augmented matrix. In step 1, we divide row 1 by 2 to make the leading coefficient 1. Gaussian elimination involves a series of such systematic transformations to simplify the matrix, and eventually make it conducive for back substitution. In the example, we continue with the Gaussian elimination process. In step 2, we add 3 times row 1 to row 2 to eliminate the coefficient below the leading one. With this transformation, the augmented matrix is now in row echelon form. This is a significant milestone in the Gaussian elimination process, as it simplifies the system and allows for efficient solution through back substitution. A matrix is said to be in row echelon form if it satisfies the following conditions. 1. Non-zero rows, all zero rows are at the bottom of the matrix. 2. Leading entry, in each non-zero row, the leftmost non-zero entry is 1, and this one is called the leading entry. The column that contains this leading entry is known as a pivot column. 3. Row position of leading entries, the row in which the leading entry occurs is below the row of the leading entry in the preceding row. 4. All zero rows at the bottom, any row containing only zeros is placed at the bottom. Back substitution is a systematic method used to solve a system of linear equations, particularly when the system is in row echelon form or upper triangular form. It's a process of working backwards, starting from the last equation and solving for the variables by substitution, hence the term back substitution. Solving systems of linear equations using matrix methods offers efficient and versatile approaches. One method is the matrix inversion method, where we multiply both sides of the equation Ax equals b by the inverse of A, if it exists. This yields the solution vector x by itself, making it a convenient approach. Another method is LU decomposition, which involves expressing the matrix A as the product of a lower triangular matrix L and an upper triangular matrix U. This decomposition simplifies the process of solving linear systems by transforming it into two simpler systems, one lower triangular and the other upper triangular, which can be solved sequentially. An upper triangular matrix is a square matrix in which all entries below the main diagonal, including the diagonal itself, are zero. A lower triangular matrix is a square matrix in which all entries above the main diagonal, including the diagonal itself, are zero. With LU decomposition, we can rewrite the system X equals B as LU X equals B. By solving the two systems successively, we obtain the solution vector X. This method is particularly useful for solving large systems efficiently, as it minimizes the computational effort. Matrix methods are vital in AI, especially in tasks like optimization and regression, where systems of linear equations frequently arise. Understanding these methods equips us to tackle complex problems effectively. The ability to solve systems of linear equations is not just an academic exercise, but a powerful tool, with a broad spectrum of applications across various fields. In engineering, linear systems are used for circuit analysis, structural analysis, control systems, and more. In economics, they help model economic systems, enabling optimization of resource allocation. Physics relies on linear systems for modeling physical phenomena, solving problems related to motion, forces, and more. In computer graphics, linear systems are used for rendering, transformations, and simulations. Furthermore, in machine learning, systems of linear equations form the basis of many algorithms, especially those related to regression and optimization. To sum up, this module has introduced you to the vital topic of solving systems of linear equations. We began by understanding how linear systems can be elegantly represented as matrices, which is a foundational concept in linear algebra and AI. We then delved into Gaussian elimination and its role in transforming augmented matrices to row echelon form, simplifying the process of solving systems. Additionally, we explored matrix methods for solving linear systems, particularly the matrix inversion method and LU decomposition, both of which are essential tools in the AI toolbox. These methods are pivotal in solving complex problems efficiently and accurately.